Namaste to everyone. I welcome you all in my YouTube video channel. Today I will deliver lecture on graph theory, lecture number 33, in which I will give the concepts of edge connectivity, vertex connectivity, separable graphs and Cut-Vertex. With the help of particular example, we wish to know what is the edge connectivity of a connected graph. We have two graphs. Both graphs are same graph. For working purpose, I have drawn two graphs. Here we see that this graph contains vertices V1, V2, V3, V4, V5, V6, and this graph also contains same vertices. And also here edges are A, B, C, D, E, F, G, H, I, J. Here also same. A, B, C, D, E, F, G, H, I, J. Let us remove the edges A and B. This is a cut set. Cut set is S1 containing edges A and B. If we remove these two edges, here we see that we get to disconnected graph. Here first component contains only vertex V1 and second component contains remaining vertices. Also the edges A and B are removed. Again we take another cut set. Another cut set is here D, E, F, G. S2 be the another cut set containing edges D, E, F, G. If we remove edges D, E, F and G, we get two disconnected components. So in this way we may get different cut sets such that they will disconnect the graph into two components. Among these cut sets, we have to take the smallest cut set, means the cut set which contains minimum number of edges. Here the cut set contains minimum number of edges be 2. Then we say that the edge connectivity equal to 2. In the first cut set S1 contains 2 edges and other cut sets contain 2 or more than 2 edges. So the smallest cut set contains 2 edges and this 2 is called edge connectivity of the graph G. Now we define edge connectivity of a connected graph. Edge connectivity of a connected graph is defined as the minimum number of edges whose removal from the graph partitions the graph into two components. In other words, we may define this: the number of edges in the smallest cut set is defined as edge connectivity of the connected graph. Here we give an example. The edge connectivity of complete bipartite graph K23 is 2. Here this is complete bipartite graph K23. Here we have two vertices V1 and V2, and this side three vertices V3, V4 and V5. All vertices of left side are connected with all vertices of the right side. Here we see that if we take a cut set like this, means if we delete these, we get two disconnected graph. Here first component contains the vertex V5 and second component contains other vertices. So edge connectivity of K23 equal to, here we have removed two edges. These two edges have been removed. So here we write minimum of 2 and 3, that is 2. Similarly, for KMN, complete bipartite graph, the edge connectivity of KMN equal to minimum of M and N. Next example, complete graph having n vertices. The edge connectivity equal to, since one vertex is connected with remaining n minus 1 number of vertices by edges, if we delete n minus 1 edges, then we get two disconnected graph. Therefore, in this case, we get edge connectivity equal to n minus 1. Now, we want to know what is vertex connectivity of a connected graph. Let we have two graphs, here graph G1 and here graph G2. First, we speak about the graph G1. Here we see that if we remove vertices V2 and V3 means we remove all the edges with these vertices. We get two disconnected graph. In the first component, we see that the vertex V1 be present, and in the second component, vertices V4, V5 and V6 are present. These are two disconnected graphs. So, if we remove two vertices, then we get two disconnected graph. In this way, we may remove the vertices and we get the disconnected graphs. In this process, if minimum number of vertices are removed and we get two disconnected graphs, then that minimum number of vertices, the minimum number is called the vertex connectivity of the connected graph. Now we speak about the graph G2. Here, if we remove V3 here and its connecting edges, then we get two disconnected graph. Therefore, here we have removed only one vertex. Therefore, minimum number of deleted vertex be 1. So, vertex connectivity of this graph is 1. Now we define the vertex connectivity of a connected graph. The vertex connectivity of a connected graph G is defined as minimum number of vertices whose removal from graph G leaves the remaining graph disconnected. The vertex connectivity is meaningful only for graphs that have 3 or more vertices and graph is not complete. Now we give some examples. Vertex connectivity of any tree is 1. Let we have tree here V1, V2, V3, V4, V5 and V6 V vertices of the tree. If we remove any one vertex, let we remove V4 here. V4 with its edges and we get disconnected graphs. Next example is vertex connectivity of complete bipartite graph K23 is 2. That is vertex connectivity of K23 equal to minimum of 2 and 3. That is 2. Similarly, vertex connectivity of complete bipartite graph Kmn equal to minimum of M and N. Now we define separable graph. A connected graph whose vertex connectivity is 1 is called a separable graph. Now we give an example. Here we have a graph G. This is a connected graph. Here we see that if we remove this vertex V from the graph, we get two disconnected graph. Means we get two separate components, different components. Therefore, by removing only one vertex V, the graph is a disconnected graph. That means vertex connectivity of graph G equal to 1. Therefore, this graph is a separable graph. If we remove this vertex V along with the edges, we get two disconnected graphs. Hence, this graph is a separable graph. Now we define non-separable graph. A connected graph whose vertex connectivity is not 1 is called a non-separable graph. Here we have an example. This is a graph G. Its vertex connectivity equal to 2. Therefore, 2 is not equal to 1. Hence, this graph is non-separable graph. Now we define cut-vertex. A cut-vertex is a vertex in a separable graph whose removal disconnects the graph. Cut-vertex is also called articulation point. A given separable graph can have more than one cut-vertex. Here we have an example. Here we see that if we remove vertex V, then the graph is changed into two disconnected graphs. Therefore, the vertex connectivity of this graph is 1. And therefore, this graph will be called as separable graph. Here we see that in the similar manner, if the W vertex is removed from the graph, then also the graph is changed into two disconnected graphs. Therefore, in this case also we may say that the vertex connectivity of the graph is 1. That means this graph is a separable graph. And for this reason, this V is called a cut-vertex, and also W may be called as a cut-vertex, because if we remove this vertex, the graph is changed into two disconnected graph. Now we solve a problem. Problem is prove that in a tree every vertex of degree greater than 1 is a cut-vertex. Solution. Let we have a tree T. Shown in figure given below. Here vertex V1, here vertex V2, vertex V3, vertex V4, vertex V5, like this. Here degree of vertex V2 equal to 3. That is, degree of V2 is greater than 1. Since the degree of V2 is greater than 1, therefore at least two vertices V1 and V3 are adjacent to V2. If this vertex is adjacent to V2 and V1 vertex is adjacent to V2, then degree of V2 is at least 2. We get a path from V1 to V3 via V2. If vertex V2 is removed, this is removed, then vertices V1 and V3 will lie in different components. And we will not get a path from V1 to V3. Therefore, removal of V2 disconnects the graph. Therefore, vertex connectivity of tree T equal to 1. Therefore, T is a separable graph. And V2 will be a cut vertex. Proved. Thanks for watching my video. If you are satisfied with my presentation and contents, then please click on like button and do subscribe my YouTube channel. Thank you.